Hello and welcome back to Higher Maths Differentiation, graphs of the derivative. So I've just got two examples to go through just to follow on from the previous video. The curve y equals f of x, shown below as a cubic. It has stationary points where x equals 1 and x equals 4. Sketch the graph of y equals f dashed of x. So we need to sketch a graph that describes the gradient of this original graph. So what I'm going to do, and what you guys should always do, split this graph up into different sections. So here's a turning point here. So we have a minimum turning point and a maximum turning point. So remember, these turning points will, on the graph of the derivative, the graph of the gradient, the graph that describes the gradient, here the gradient's 0, here the gradient's 0. So on the graph below, at this value of x and at this value of x, we will have the roots, because the gradient is 0 at those points. This graph describes the gradient of the line of the curve above. So here's a gradient of 0. So in this graph, the height must be 0, because this is describing the gradient. Okay, it can't be up here, because that would be saying, well, the gradient's 1 or 2 or a positive value on the graph above, which it isn't, it's 0. If it was lower down, it'd be saying, well, the gradient's negative for this value of x, which it isn't. The gradient is 0, so it must be a root. It must lie on the x-axis. Right, so we have a negative gradient, then a positive gradient, then a negative gradient. So on my graph below, which is going to describe this, I need to show that it's a negative gradient. So remember, this y-axis here describes the gradient of the original graph. So let's look at when x is 0. When x is 0, obviously it's a negative gradient. So it might be negative 3 or negative 4 or negative 5 or negative 2.96, who knows? So here, when x is 0, to show that there is a negative gradient up here, I need this to take a negative value. Okay? So the confusing part is the fact that this line is increasing, but showing a negative gradient. Now, if we put some numbers on this axis, if I went negative 1, negative 2, negative 3, negative 4, then that would just describe the gradient up here. So when x is 0, there might be a gradient of negative 4. When x is negative 1, it's even steeper, so there might be a gradient of negative 7, which there is. There's a steep negative gradient, it's becoming less and less. Now, between the first and the second turning point there, we have a positive gradient. So that will need to be a positive value here. So again, if we put numbers on here, we might go 1, 2, 3. So we've got a gradient of 1, then a gradient of 2, then a gradient of 3, then a gradient of 2, then a gradient of 1 again, and back to a gradient of 0. So we hit a turning point and it's shallow, then it gets steeper, then it gets less steep, and it flattens off until it gets to a gradient of 0 again. Okay, so if I just pick this point for x here and look up, it's a positive gradient on the original graph. Let's have a look. Yes, it is. And then afterwards, we've got a negative gradient after the maximum turning point. So on the graph of the derivative below, that needs to take a negative value, which it does. Right, let's look at one more example. The graph below has stationary points at negative 1, negative 3, and 3, 0. Sketch the graph of y equals f dashed of x, given the original graph is a quartic, which is power 4. So if I differentiate quartic, I will get a cubic. So mark on the stationary points, and they need to be represented by roots. Split up the curve, so I've got a negative gradient, then a positive gradient, then a positive gradient again. So in terms of the graph of the derivative, I need to be below the x-axis, above the x-axis, then above the x-axis in those three sections. So I know what a cubic looks like, so I'm going to be coming up. So rising towards a turning point, then above, but back down, and then above again. Okay, so again, one more time. Turning point will be the root and the root. Any negative gradient, I need to be below the x-axis here. Any positive gradient, I need to be above the x-axis, but I can go up and come back down because I'm still above the x-axis here, so I'm still representing a positive gradient at this point.